Welcome everybody to this session. I hope it will be very insightful, and I would like to encourage an open discussion in order to ensure that most of us, well, all of us, understand water movement in the soil better, and in the end of the day, it can lead to us making better decisions when we are scheduling, and then also when we are planning new developments to ensure that our spacing and delivery rates are selected correctly. So please also note that we will record the session, and it will also be made available afterwards. So if I go into a little bit more detail, you will have the opportunity to go and have a relook at it should you need to. Marika also will handle the Q&A session afterwards. So if you have any questions, you can ask it in the Q&A section. A little bit about myself. So I'm Jovan Erasmus, studied BSc Agric at the University of Pretoria, where after I worked as an agronomist for a precision agriculture company based in Dunedin, with main focus on citrus, avos and macadamias. And then since 2020, I was an agronomist at Netafim up until now. So the agenda for the day, first we'll look at the concepts regarding soil water movement, and then we'll go into some case studies. So we'll look at soil texture, structure, water content, distribution in the soil, then some test case studies, and then how do we take all of that information together to decide on our dripper spacing and delivery rates. So what all affects the movement of the water in the soil? As you know, soil is a complex system. There's a lot going on in there. So we're going to dive into the soil texture, structure, classification, chemistry, organic matter, water content, and also water quality. Soil texture. Everybody, I'm sure, has seen this triangle when referred to soil texture. What we have here is, depending on your percentages, sand, silt, and clay, we can give your soil a name, soil texture, which then leads us to understand a few things about that soil and how that soil will distribute water, and how that soil will obviously hold on to water, and how the roots will grow and all of that. So for reference, have a look at that. If you have a look at the size distribution of sand, silt, and clay, I hope it's big enough there, but there's a big difference. Obviously, your sand particles are larger, and they can be anything between 0.05 millimeters to 2 millimeters. Anything larger than 2 millimeters is considered gravel and rocks and other matter. When we look at soil, minerals specifically, everything smaller than 2 millimeters. And then if you zoom in a lot more, you can see that silt is 0.02 millimeters to 0.05, and then a lot more smaller than that would be your clay particles. You can also see in that picture that your clay particles tend to pack slightly. Obviously, you can't see clay particles of your bare eye, and they tend to pack in horizontal or vertical sections, if I can say it like that. And your salt and clay, your salt and sand particles tend to be more roughly distributed throughout your soil profile. So what does the soil texture tell us about the water holding capacity and water, what do you call it, the movement of water in the soil? So first of all, the water is held on the surface of those particles. So as you can see there, you'll have big particles which would be considered your soil minerals, and then in between there's areas we call pores. But your water goes and it attaches itself to the surfaces of your water. It cannot penetrate into your sand or silt or clay particles. So air and water moves in between the particles, and the water is out on the surface. So when we look at the size distribution, it's important to note that there is a surface to volume ratio. An example of that would be shown here, where the larger your actual particles. So in your mind's eye view, the left block as sand and silt and clay, and you can imagine that there's a lot of volume inside of that first cube that is wasted, and the water can only sit on the outsides of that cube. If you break it down into smaller pieces, the water can go in between, and there's a lot more surface area where water can attach to, and that then leads to your heavier clay soil having higher water holding capacity compared to your sandier soils having lower water holding capacity. So smaller particles have more surface area and can hold more water. And then we're going to look at a bit and how does the soil hold on to these water particles. So here's a very nice infographic of that concepts that we talk about a lot. So the main forces that work on water and on soil is called adhesion and cohesion. To put it simply, cohesion is how the water particles bind together and how they hold on to each other. And then your adhesion would be how your water particles attaches itself to other surfaces that are polar or charged, as in your as in soil particles. And that adhesion forces is what causes the water to move in your soil. So some everyday examples of cohesion and adhesion would be, if you see the water droplet there on the leaf, it forms a little bundle by itself. So there's very strong cohesive forces there holding that water droplet in a bundle. And an example of adhesion, there's obviously cohesion and adhesion in that picture, but that surface is a glass window, which is also polar and charged, which attracts the water molecules and attaches and spreads out a little bit more compared to what you see on the leaf. So this is another infographic of what actually is going on there. So you can imagine the soil is that brown there at the bottom, and then a water particle, water droplet on that soil surface, where your cohesion forces holds that water particle together, and then there at the bottom, the adhesion forces is the actual attachment between the soil and the water. So this is just a little bit of chemistry and the polarity of water. So everybody knows that positive and negative ions and everything that's positive and negative attracts itself. So when a water molecule forms, it arranges itself in this form here, where the two positive hydrogens move towards the one side, and then it causes that polarity. So that polarity is important. That polarity is important because that helps the positive side will attach to the negative soil side of the soil particles, and then the negative side will then attach. That's where the cohesion. So the next water droplet next to its positive side will connect to the negative side, if that makes sense. And if you look in your soil and in your pores, you can see there's again an example of how the water just sits on the outside surfaces of that water sample. So there's a lot of adhesion factors there. And then if you zoom into that a little bit more, you can see that that water, there's a combination of adhesion and cohesion going on there, and that water is held there in the air, and it's not draining past, obviously in the soil, it's not draining past those two soil particles. So another example of how capillary action works. So we know capillary action is important for the movement of water either sideways and also upwards in the soil. So an example there is if you take a straw and you put it in a glass of water, you'll always see that because of that surface adhesion factors, the water tends to pull up into that straw. Obviously, you need a see-through straw to see it, but that is the same principles that move water in the soil and ensures that the soil can hold on to specific amount of water that you require. So soil texture, just to sum it up a bit, we know that clay particles are negatively charged, and that attaches with hydrogen bonds through adhesion to your water molecules. And then the soils consist of different sized particles mixed together. So you won't have a clay soil or a sand or a silt. Those soils are mixtures between different amounts of these different textures, but they are mixed roughly. I've got some pictures that will follow to explain that better. So smaller particles have more surface area. That means that they will hold on to more water. Larger particles, less surface area, and hold on to less water. Then, as a part of the soil matrix and what's going on in there is also your soil organic content. So soil always consists in a combination of minerals, air, water, and organic matter. And I'm sure a lot of you have seen this or similar infographic as this, but the soils generally exist in roughly those ratios, and you can't do much towards the percentages of the minerals. In South African conditions, your 5% organic matter might be on the higher side. We generally, I would say it's mostly below 2, even below 1%. And then your ratio between air and water, that is always constant. Not constant, that fluctuates. So the more air you put in, the more water you put in, the more air you drive out. And then as your soils dry out, more air comes into your root zone and then obviously your soil. So organic matter in the soil, what is it? It's plant, animal, microbial residues at various stages of decomposition. Organic matter can be categorized as living organisms, fresh residues, active organic matter, and stable organic matter. So living organisms, we know what they do. They're mycorrhiza, they are all the little creepy crawlies, earthworms, things like that make up of the organic matter. Fresh residues would be fresh leaf litter, not yet broken down. Active organic matter would be semi-broken down, but already in the process of releasing nutrients to your roots and to your plant. And then your stable organic matter, that aids a lot in your, well, that's already well broken down, and that aids a lot in your structure of your soil, which can obviously increase your water holding capacity quite a lot. So a breakdown of organic matter that you can typically find in the soil, and this is considered a healthy soil. If your soil is not healthy, you tend to have less or unbalanced ratios in your soil organic matter. But it's been noted because of the small pores that you find in your organic matter and the way they distribute in the soil, they can actually, if you have good high levels of stable organic matter in your soil, your water holding capacity gets greatly increased by factors of up to 10-fold when you have more organic matter in your soil. Right, so what does it do? It improves your water holding capacity, and then because it's forming more stable structures and aggregates your soil particles, which allows for better structure and more evenly distributed pores, and also more pores specifically. Increasing your infiltration rate of your soil, you can have a large amount of pores, and they also, the organic matter is also charged surfaces, which will then help to hold onto water more. Soil structure. So soil structure is, soils consist of a combination of different size particles and also organic matter. So the soil structure, the whole idea is how is my texture and my organic matter put together to form my specific soil structure. As you can see there on that picture, it's a complex system. You will have sand particles, the big yellow ones, and then the smaller you go, you can have silt particles, which would be the orange, and then you can have the clay particles, which would be black, and then obviously there in between you'll have organic matter as well. But as you can see, it randomly, in healthy good soils, it randomly spaces itself and mixes itself throughout the profile. So when we look at what is important for us when we want to look at how water moves in the soil, we need to understand how in this combination of obviously setup and structure, how does that affect my pores? Because the pores is the spaces between the soil minerals and the organic matter. And it's very important because your air and your water is held in these pores, and your roots also grow in these pores. The amount and sizes of these pores affect the amount of the water that can be held in your soil. Again, that previous picture just showing the pores combined with some of the soil particles, and the water is held in those pores. Yeah. Same ratios I just explained earlier. If we dive a bit deeper into pores, we get macropores, and then they are generally considered the larger pores. They are key to water infiltration and then drainage. Drainage is very important because you need to get oxygen into your soil as well in order for your roots to take up water and for your plants to be healthy. This helps us with a fast exchange of air and water. So if you irrigate, your water goes nicely into the soil, and then your air moves out fastly, and then vice versa. Your macropores, they are a lot smaller pores. They are key to holding onto the water in your profile. So your amount and the size of your pores is greatly dependent on your texture of your soil. So lighter soils or sandier soils, loamy soils, tend to have more macropores because of the large sizes of these sand particles. They can't pack together. They can't pack together as neatly as tightly as the clay particles, and then your heavier clay soils have more micropores. So these micropores are very important because they, when they are spaced in between the clay particles, they hold on to a lot of water, and that's where the plant gets its, what do you call it? I'm going to call it a buffer, and that water holding capacity. So as you can see on this picture, it's a very complex illustration. My pointer is not as responsive, but I'm going to try to zoom in on there. So if you can see, there's some blue lines there. So that would be in a soil particle where there's some clay minerals, and then you'll have your micropores in there. And your macropores would be your bigger channels where air and water will move freely and fast. And then you've got organic matter, you've got roots, everything going on in this complex system. Okay, compaction. So compaction is a process where the density of your soil is increased. Let's explain that. So the density of a soil is your mass divided by your volume. So if you have a known volume of soil, the heavier that volume, the higher the density, and then vice versa, the lighter that volume, the lower the density. So some examples here of typical soil densities that you'll find is sand particles will generally have a higher density compared to clay particles, which will have smaller densities. And the main reason here, it might sound reversed, but there is a lot more micropores contained in more heavier soils, clay, salty soils, clay loam soils, compared to your sandy soils, which have all of these macropores. And if you compact a sandy soil that's already quite dense, those macropores tend to shift, and then that soils tend to compact easier compared to your soils where you have more of these micropores. So compaction, soils particles are forced tighter together, and then that leads to us having less pores to move air and water. So you'll have very good drainage and air movement in a soil that is not compacted compared to us pressing everything together. The air and the water can't move through that. And that causes issues. I've got some nice examples later on which explains what happens when you have a compacted soil. It greatly reduces the water movement, and then it greatly reduces your root growth in your soil as well. So how do we measure compaction? You can see there's a penetrometer and a little graph. From a lot of research, we know that root growth stops above 2000 kPa, cannot force itself through compacted soil. So once that compaction reaches that high resistance, root growth and water movement becomes highly impacted. You can also dig profile pits, and you can feel compaction quite easily. And there's a good example where the root actually does not want to move deeper because of that compacted layer found in that soil. And the water does exactly the same thing. It doesn't easily want to penetrate that compacted zone, and that makes your scheduling and decision making a lot more difficult. One of the greatest, biggest culprits when it comes to soil compaction is wheel traffic, and it's one of the only things that we can actually try and control. So as you go more towards regenerative agriculture, people tend to pay a lot more attention to not driving too much on where your actual roots will occur. An important fact to remember is if you did very good soil preparation and you did a nice deep rip, the first time you drive over that soil again, it can compact back to 70% of its original state. So then another important part is soil layering. So it occurs when different distinct layers exist in a profile, generally due to large textural differences between the topsoil and the subsoil. So textural differences here, we can have a sandy topsoil with a abrupt transition to a heavier clay, and then what happens is the water does not want to move over that large textural difference, so it will fill the profile there at the top where it moves easily, and then only after that it can move into that second layer, because the infiltration there on that second layer might be a lot lower or slower. This can cause to a lot of irrigation issues where you tend to over-irrigate that subsoil, but your roots can't go down, and you can't manage your air and water, ratios in your topsoils. So this is an important factor to consider. Also, compaction tends to behave a lot the same as soil layering when it comes to water movement, where you'll see exactly the same distribution of the water and the issues with that. A little bit on soil chemistry. I'm just going to touch soil dispersion, which is caused by very high sodium levels in the soil. So what does the sodium do? It binds to the negatively charged clay particles and it forces these clay particles apart. So as we saw in previous pictures, our clay particles obviously are negatively charged and then they are packed quite neatly, as you can also see in this example here. So normal soils tend to have a lot of calcium, and calcium is good for the structure. As you can see there on the right-hand side, the water can move easily through those macro pores, and then there's a lot of micro pores in between there which can hold onto your water. Generally, with the calcium content, it helps the soil to form better aggregates and just allows your soil to breathe. When you have a lot of sodium, because there's only one positive charge there, they tend to bind to very fast to the clay particles, and then they push away on its other. The calcium have two positive sides, so they can actually attach to both sides of the soil minerals. So a very nice example of how you can practically see if a soil is sodic. On the left, you'll see the soil has good structure. If you put it in water, that structure remains. But this dispersion caused by the high sodium levels, as you can see there, as soon as you add water to it, it pushes those particles apart. And then it causes a lot of issues when, obviously, it creates a lot of micropores, but too many. Everything needs to be in balance. But with this high amount of micropores, specifically at your surface, you tend to have very slow infiltration, very low aeration, and very slow drainage. And some examples of what you can see there is crusting, which is a big concern with irrigation, because you'll get a lot of runoff and you don't get infiltration into your soil. Then soil water content. So all aforementioned factors are acting together in this complex soil matrix, and that everything working together will give you your soil's water holding capacity. I did not mention earlier, but along with your soil texture, you can also have rocks and stones and things like that, which also greatly impacts your water holding capacity. But I'm not going to go into that in this presentation. But just know that with rocks and stones, anything larger than 2 millimeters will generally reduce your water holding capacity in your soil. So when we talk about water holding capacity, we would express it as millimeters per meter. So that meter is a depth, and millimeters, does not have a volume attached to it until we add a specific area. So let's think about if it rains, and if you have, when we talk about rain, we talk about 1 millimeter or 10 millimeters or 20. Just to bring that into perspective with how much water that is. So 1 millimeter on 1 square meter would be considered a liter. If you look at that millimeter per meter factor there, so this millimeter is actually a thickness layer. So if that 1 liter on a square meter, it will actually have a 1 millimeter thick layer of water. So as you increase the liters, that layer of thickness will just increase. But as we know, a soil is not only consistent of this. That's not what a soil looks like. A soil looks more like this, where there's pores and minerals, and there's less space for water in that specific sump. So this is general guidelines that I work on. If you consider heavier soils tend to have higher clay percentages and more micropores, as I've mentioned. They tend to have water holding capacities of between 150 to 220 millimeters per meter. Medium soils, your loamy soils, some sandy loams will have 90 to 150 millimeters per meter, and then lighter soils can have 40 to 90 millimeters per meter. Remember that your stone fragments can also impact this water holding capacity greatly. So this is considered if your soil is 1 meter deep. So for the theory of it, we will consider our soil uniform 1 meter deep for the calculation. So you've all seen this pictures quite often, I hope. We know soil can exist, obviously soil water status can exist in a few states where saturation is if you have a lot of water there and there's free drainage of water taking place. And you can also see there's no air left in that specific sample. If you reach field water capacity, also called your upper drainage limit, that is when all your free water has drained past and air and oxygen has removed back into your soil profile, and your soil will remain steady in that state due to obviously the cohesion and adhesion factors and the forces of that soil particles holding onto that water. And this is a state where water is highly available to a plant because of that good ratio between air and water maintained in that soil. And as you start, your plant uses water, your field water capacity, obviously the soil content will reduce, and then until you reach a permanent wilting point. Now, you can't see it as clearly as I can, but on those little soil particles, there is still some water attached to it. The soil is not completely bone dry, but the plants do not have access to that water because of these forces that the soil hold onto that water becomes more as your soil dries. So if we take that into consideration, if we find a soil at field water capacity 1 meter deep, heavier soils, it can take about 180 liters per square meter to fill that profile. So that was considering your profile was was bone dry, fully empty. 180 liters will fill it up to field water capacity. Same for medium, 120. So that's obviously just an example there, and do not take these numbers and apply them to practice. There are ways to figure this out for your own specific situations. So let's look at the larger scheme of things. Let's scale it up a bit, because talking about 1 square meter might sound a bit small. So generally, when we talk about agriculture, we talk about 1 hectare in South Africa, or in scales of hectares. So just for comparison, everybody knows that that 1 hectare equals 10,000 square meters. So if you take the same calculation that we did earlier and say 1 liter per square meter is 1 millimeter, then it will also be true to say that 10,000 liters per 10,000 square meters is also 1 millimeter. Thus, 10,000 liters per hectare is 1 millimeter. So if it rains 50 mils outside, you can just do some calculations and see how much water actually falls. And then you can can imagine for your calculations, and you can imagine how much of that water actually goes into your soil for your specific root zone. And generally, we don't have root zones that are 1 meter deep. We generally work with 60 centimeters on most tree crops, and then when you go to vegetable crops, it's mostly between 50 and 30 centimeters. Even cabbages, you can work with only 20 centimeters. So just consider the amount of water it actually takes to refill your soil to that specific water holding capacity and field capacity. So now we've touched a lot on all the higher level factors that have all influence on how your water distributes in your soil. Now we're going to look at some practical examples and some case studies that we've done over time, which obviously helped us to learn a lot about how your water actually moves in your specific soil when you take into consideration everything that we just discussed. So first of all, water distribution. This is a simple way of understanding drip irrigation, where you actually relying on your soil's physical characteristics to move the water outwards. As you can see there, we're putting the water on one spot, and then that capillary action and the adhesion forces in your soil moves your water wider and wider and wider. So what you generally find is while you're irrigating, you'll have a ratio between wet and dry. And also remember that everything in life tends to want to move towards being in balance. So if I just irrigated and I left it and there's no roots that will use the water, this ratio that exists during normal scheduling will tend to even out, and you'll have uniform water all over your profile. But this is what we generally find when we look at drip irrigation. And then this is also important to consider when you're making your scheduling decisions or your dripper spacing decisions, is to understand this width and depth relationship in your specific soil and understand that there's also a ratio while you're actively scheduling. Same ratio that I mentioned now. So as your water content increases, your oxygen leaves your root zone. So there's always a ratio between oxygen in your root zone and then also water. So as this evens out, the oxygen will come back into the soil, and then that will also even out in time. So this is very simply explained. When we have heavier soils, we tend to see wider water distribution of underneath a dripper. And then when you have lighter soils, you tend to have narrower, deeper water distribution. So what affects the water distribution? So first of all, as we've discussed earlier, the particle size, distribution, and then obviously the soil structure affects your soil's infiltrability, hydraulic conductivity, water retention, and then porosity. So these are all factors that we have discussed previously, and they are all processes that work together that determine your specific situation. But infiltrability is when a flow, when your flow of your emitter is higher, or your application rate of your irrigation system is higher than the soil's infiltrability, the water tends to spread horizontally close to the surface quite a lot, and it moves into your soil quite fast. This can lead to ponding, runoff, and also erosion issues. So heavier soils, if your soil is heavy clay, you can have very low infiltrability, and then situations where you have sodic conditions that disperses your soil can also have very low infiltrability. Then ponding, the water application rate exceeds the infiltration rate of the soil, thus the free water ponds can form, and then this will lead to more horizontal spread and leads to more risk of exposure to runoff and specifically evaporation directly from the soil surface. So you want your water to move into your soil to avoid any of those other risks. Then we can look at saturated hydraulic conductivity and gravity. So saturated, okay, let's start from the top. Gravity, we all know how gravity works, and it also has a major effect on water. And that effect doesn't stop at the soil surface. Even inside the soil surface, your gravity pulls your water downwards. Then you have capillary action, which helps with the horizontal distribution of the water. So what we're actually looking for is a balance between your gravity and your capillary action in order to get your water into your soil, but then not having it leach past the root zone. So that's where we need to find the perfect zone to work in. And that's why dripper spacing and delivery rates become very important. Then if you look at saturated hydraulic conductivity, that is the ability of water to move in your soil based on a water content gradient. So as I mentioned earlier, water tends to everything in life wants to be in balance, and water is the same thing. If you have high concentration of water right underneath your dripper, you will reach a saturated zone there, and that saturated zone will start distributing the water out of that. So if you are considering filling a cup and you adding a cup, the water is going to remain in that cup. But if I overfill that cup, the water is going to start moving towards the next, and fall out and move away. So that exactly happens in the soil. We need to fill all the pores, and then only can the water move towards the next layers of the soil, and then obviously distribute either down or horizontally. So water moves from wet to dry, and then the wetter the soil, the more and the faster the water moves, because if you have dry soil, you first have to fill those pores close to the center, and then once they are filled, they only start moving outwards. So this becomes important when you initially start scheduling on a dry profile. It will take a lot of hours to get your soil full and at capacity and to get a specific distribution. But then in actual scheduling, because you're never going to dry out the soil that much, the water distribution will be horizontal, will move horizontally a bit faster. So again, the same situation there. Only once it's saturated underneath that dripper can the water move. And then we'll always understand that there is a ratio towards wet and dry. And then one of the nice things that we like is the water tends to, obviously these, I'm going to go back and forth so you can see, oh, sorry, wrong button. So as you can see, as your plants use water, that ball shrinks and expands as you irrigate again. So everywhere in that root zone, at some point, you'll have the perfect ratio between wet and dry, and then obviously the perfect ratio between oxygen and water for your plants to actively take it up, if you schedule correctly, obviously. So I spoke a bit about these saturated circles that form underneath the dripper. So you must also remember that I'm showing you everything in 2 dimensions, but what actually happens in your soil is a 3-dimensional water movement from these saturated circles. So if your soil has low infiltrability, what you tend to find is that you have more spread towards the surface, and then you find that wider secondary spread from that saturated circle outwards. If you have very high infiltrability, water moves into your soil faster, you have less, you have a smaller saturated circle or a narrower one, and then the distribution from that saturated circle is generally narrower. When you combine a very high emitter flow rate to a soil that's got a low infiltrability, this is what tends to happen. You tend to find ponding quite fast, and you struggle to get depth into that soil in that situation. When you have a lower flow emitter, so when I mention lower flow emitter and higher flow, traditionally we used to work with 4 liter an hour drippers, even 8 liter an hour drippers, and 3 liters. Now, as technology improves and as our understanding of water movement and infiltration and all of that improves, we gradually move towards lower emitter flow rates in order to get a more balanced infiltration into that soil, and then a more balanced horizontal distribution across various different soil profiles. What we must also consider here is to find that balance. If you have a very low infiltrability soil, then your gravity forces that pulls on that water can exceed your capillary forces with a high emitter flow rate. So that tend to move the water in a narrower band downwards because of that gravity forces pulling. So the lower flow emitter also helps us with low infiltrability soils. On high infiltrability soils, the low flow emitter also helps us to give your capillary action chance to move some of the water away before you saturate that circle too fast, to help us to control that water easier in that top root zone where you are aiming to use it. So low flow delivery almost never exceeds the infiltration rate of the soil. You can find very good infiltration on most soils, and then gravity and capillary action forces become more equal. So your soil water-air ratios are kept more constant throughout the wetted area. What we see there is again that balance, and now that ratio of air and water continuously moves. We must always consider where we want to be in our specific profile, in our root zone. There's going to be a little bit of saturation underneath your dripper, but as you move away from that dripper is where most of your water uptake is going to be, and then you never want to go as wide as permanent melting point, because that will lead to a lot more stress on your crops. So if we look at some examples of tests that we did over the years on different soil types, I'm just going to look at 2 examples to see how in practice can we figure out what is going to happen in our soil. So this is a setup that we use if there's no irrigation system already in place. It's very simple. We've got a bucket at a specific height, and then a dripper on a specific point in the soil that will drip all the water that we add into that bucket. So we tend to set up a test like this. We'll have 3 liter bucket, a 6 liter bucket, and a 9 liter bucket. And then depending on the emitter at the bottom, you will either have a 0.5 liter an hour flow, a 1 liter an hour flow, or a 2 liter an hour flow. So this is a test that we do on bare soil. Mostly we like it if the soil becomes dry, because if the soil is dry, because we need to Sorry, my throat is a bit dry. If the soil is dry and we physically need to see the differences in that water distribution, it helps quite a lot. In your scheduling situation, what I can recommend is that you run your irrigation system that you have for a certain amount of hours, and that will lead to you understanding how your water moves in your situation. So this is an example that we did there in Zanin on newly made ridges with those buckets set up like that. And then we open the profiles and we physically go and measure that width and depth of that distribution of the water in that soil underneath each bucket. What we come up with is a graph looking like this, where the blue would be 0.5 liters per hour, the red would be 1 liter an hour, and 2 liter an hour would be the green. As you can see, what we tend to find is that with the lower flow emitter, we tend to see a little bit more horizontal water movement compared to deeper movement as seen on the 2 liter an hour. And that is everything that we discussed has an impact on what's happening in your soil. If you look at the 6 liter bucket, so that would be 12 hours of irrigation on the 0.5 liter, 6 hours on the 1 liter, and 3 hours on the 2 liter. There you can again see the lower the flow, the more horizontal spread we get. Reasons for this is that capillary action gets a chance to move the water horizontally faster than your gravity force is pulling it down. 9 liters on the mean. At a point when your layers meet, the ratios tend to balance out a bit. But for comparison there, that is almost a 15 centimeter difference on either side, 10 to 15, which can make a big, can have a big impact on your actual dripper delivery rate and spacing that you choose. So this was a very sandy soil. You can't see it as well. There's a darker bit in the middle, a lot deeper water movement on the 2 liters compared to a lot wider that we found on the 0.5, even on a very sandy, highly leached soil. So some tests I did in Nelspruit showing the same thing. And then what we found there was actually, when we moved to the next ridge, there was subsurface water that is running underneath that ridge that actually affected our test. But that's also a good consideration that if you have subsurface water that can come into your root zone, that will greatly affect your management of that specific zone, and you need to decrease your management root zone. Compaction. Some example we found in Nelspruit, the ridges were built without ripping. He just used the excavator to build the ridges on top of the soil there, and we found that extremely hard layer, which we struggled to dig through. As you can see it there on the profiles that we dug, it's very clear that compaction was everywhere. We also did some compaction tests. Oh shit, that video is turning sideways. That's not nice. Anyways, it draws a nice graph of depth versus that resistance that I spoke about earlier. And what we saw in this situation is at 30 to 40 centimeters on all those ridges that were so compacted, we found that compaction. And when we did our drip test there, obviously before we did the drip test, we didn't know about the compaction. And on the 3 liters, very shallow, we didn't see any issues, we didn't see any problems. But once we started seeing, once we had the 6 liter buckets, we started seeing some very interesting things which actually correlate well to what happens in practice if you have compaction and then also layering. So you can see there, the low flow emitter never actually went past that compaction zone where on your the 2 liter an hour dripper, you started getting secondary movement of secondary distribution below that compaction layer because of the saturation zone increasing so much that it forced water into that second layer a lot faster, which makes scheduling extremely difficult. As you can see there on the bigger ridge 9 liter, we also had a massive horizontal distribution on even the 2 liter side. And then just a picture to explain to you the graph that we just discussed. This all makes scheduling decisions more difficult, but we need to know what we deal with, and then we can know how to manage that specific system. So if I look at obviously some tests we did in Lexiteli, I'm going to compare some distributions in these soils and then how to determine your dripper spacing. So I'm going to take a look at this 6 liter an hour. As you can see, again, we get a little bit better distribution with the 0.5s compared to the others. But I'm going to zoom into that 1 liter an hour one with the 3 liter bucket. So it's actually this one that we're going to use to make some calculations. As you can see, it only moves in 40 centimeters into the soil. It's not a lot of water. Yeah. Okay. Some examples. So if you consider vegetables tend to have a very shallower root zones compared to tree crops. So my example is going to focus on vegetables, and I'm going to take the test results that I had on that specific soil, and then I'm going to make some decisions here. So as you can see, if my drippers are spaced every 30 centimeters and I irrigate for that 3 hours, I will get a very nice overlap of water there, but there might be some water that goes past my root zone. So anything that goes past your root zone is considered a loss. And always consider this ratio that we have here, where it's going to be slightly wetter on in the center at the dripper, and then the gradient moves outwards. So for this example, 3 hours irrigation would have gone a little bit past my root zone. So I estimate that probably 2 hours would have been enough to manage that water in that specific root zone, depending on that horizontal and depth movement that we got. If I move those drippers to 40 centimeters, what happens now is that we need to irrigate longer hours to actually get good overlap in the center, but still we're going to go past our root zone, which can lead to us losing fertilizer and moisture. And then again, consider this ratio where it's going to be wetter here in the middle, and as you go out, it's going to be drier. If I take the same situation and I go at a 60 centimeter spacing, you see where we start running into a problem where you're going to start, even on your vegetable crop, irrigating in pots. So this would be a better situation if you're working with tree crops where you have a 60 centimeter root zone, but you can clearly see that you have to irrigate past your root zone in order to have that match of water and then the overlap in the centers. Okay, same slide. So in conclusion, water distribution is determined by many factors. Selecting the correct dripper spacing is crucial, and then understanding your soil and water movements and your plant requirements makes it a lot easier to make these decisions. And yeah, we have a lot of experience at Netafim, and then we are more than willing to help you and assist to make these decisions. And we are open to a lot of discussions. So please, if you have any questions, I think now will be the time. Marika, I don't know if you have some Q&As there.
Thank you, Jovan. Well done. That was very insightful. We have one question. Before I ask that, you're welcome to add your questions to the Q&A or even raise your hand and I will unmute you. So Marco Paniza asks, how much must we consider the evaporative effect of radiation using low flow drippers?
So evaporation will always have a big effect. As you saw some of my examples where we tend to have ponding caused by higher flow, you have more water exposed on that specific surface. But the question can be a bit loaded as well, because if you have low flow emitters, you're going to irrigate for longer times. But we tend to see more infiltration into the soil because of the balances. So yes, you're going to irrigate longer times, but we still see the water moves into the soil better and doesn't pond at the surface. But always for evaporation, it will be advisable to have some sort of a mulch. And then as tree crops grow, your tree canopy will eventually shade that direct radiation, which will reduce your evaporation. But initially, on the first few years of an orchard, you're going to have a lot of evaporation. But comparing that evaporative losses to micro irrigation, where you wet the whole surface, there's a lot of savings still when you get to when you look at lower flow emitters. So there's a balance to be found. My recommendation will always be have a little bit of a organic cover mulch to assist.
Okay, there's a question from Divan. You can unmute yourself and ask your question.
Yes, Jovan, ek hoop ek kan in Afrikaans hierdie vraag sommer vir jou vra. Julle in die noorde het mos eintlik chocolatgrond en somerreënval. Hier in die Weskaap het ons winterreënval en ons het swak gronde. Ons sit met die probleem dat ons baie versadigde gronde het voor blom. En ons moet kunsmis insit in daai tydperk en ons moet dan tegniese besproeiings in plek stel om daai kunsmis in te kry. Die tweede opsie is natuurlik ons kan korrel kunsmis gee, maar dis ons tweede keuse. Ons wil nie dit doen nie. Ons wil die kunsmis kan beheer tot die beste van ons vermoë. So wat is daai effekte op ons wortelstelsel indien ons daai tegniese besproeiings doen? Want die redenasie is dat daai 30 minute of 'n uur besproeiing wat ons bygee nie eintlik 'n groot effek op ons versadigheid het nie, want dit is reeds versadig. Wat is jou opinie daaroor?
So thank you very much, Divan. So the question, just in short, is if you consider summer rainfall areas compared to winter rainfall in the Cape, that is always depend on your drainage that you have in your soil. So if you have free drainage and some of that excess water can move past your root zone, that technical irrigation that you're giving just to fertigate generally is at a higher EC and a very short time. So with the lower flow emitters, you tend to not add too much water to that system. But consider if you do not have drainage, then you're obviously you're going to have an issue, but your issue will be more severe than what your irrigation will do if you don't have free drainage past your root zone in that condition. So in general, with your soils being of lower water holding capacity, I'm assuming good drainage, then it won't necessarily cause an issue. You'll have a concentrated bit of fertilizer, which then will, due to the fusion, will move out again in your soil. But that's something we have to do, and as long as you don't have drainage issues, it shouldn't be a problem. Because you're adding the water to the top. So if you add a drop to the top, a drop goes out the bottom. So your fertilizer stays in the root zone.